So, we will discuss about the experiment that is determination of spring constant. So, this is the experimental setup for determination of spring constant. So, this is the spring, and what is the spring constant of this spring, that is what we will find out. Okay. So, this very simple experiment. So, this one end of the spring is attached with a solid say stand, and other end is basically used to put the weight, and will increase the weight and find out the extension of this spring. And what for, so basically for different mass, what will be the extension of the spring. So, that is what we have to measure. Okay. So, for measuring that extension of the spring, we have here the scale, we have a scale. Okay. So, this meter scale basically is the 0 to 50 centimeter, and this least count of this scale is basically 1 millimeter. So, this is the pointer which basically we will take reading of this pointer. Okay. So, as I discussed that there is a two method we use in laboratory to find out the spring constant. So, this one is static method and another is dynamic method. So, what is static method? Static method, as you know, this for spring mass system, it follows the Hooke's law. It follows the Hooke's law. So, in this case, this will apply different force on the spring. If this force is F, then if extension of the spring, elongation of the spring, or contraction of the spring is x. So, the relation between the force and this elongation or contraction of the spring, that x, they are basically proportional. So, then F equal to k x. So, k is proportionality constant, and this k is called spring constant, right. And minus sign here, this is basically in elasticity, always we consider the restoring force. So, this applied force and restoring force is basically equal. So, if we apply force, then there will be deformation of the body, and body also just apply just opposite force equal to the applied force. That force is, we tell this a restoring force. So, in this case this restoring force F and this elongation x, they are in opposite direction, that is why this minus sign comes. Okay. So, we want to find out the k spring constant. Okay. So, this spring constant k is then equal to minus F by x. So, this, let us ignore this minus sign. So, because this minus comes because of the direction of the force and the elongation. So, simply we can write this k equal to F by x, means k is nothing but the spring elongation, the force by the spring, I think it is the restoring force by the spring elongated or contracted by unit area. So, for unit change of length of the spring, how much force we need to apply. So, equal amount of force will be the restoring force. So, that is basically that force amount of force per unit length, that is the spring constant. Okay. So, we can measure this spring constant in two ways, as I told, this static method and dynamic method. Okay. So, static method is let us just discuss the static method. So, our force equation here is F equal to minus k x. So, F, as I told, I will ignore the minus sign. So, F in this case F force. So, we can use the gravitational force. So, that means, if I put weight on it, then this load, if we apply load. So, for mass m, this force will be mg, gravitational force will be mg. For mg force, so what will be the elongation of the spring, that's what we have to find out. So, basically if I vary the force, means if I vary the load, if I vary the mass, so for different mass I will get different elongation, and that elongation I will measure using the scale and this pointer, and then so then we will make a table where load versus the spring elongation. Okay. So, if you measure that one, so then you can plot the graph W or mg versus x, that is what these two we are measuring, and then it will be a straight line, and the slope of the straight line will be basically constant k. Okay. So, how we will measure that, I will just show you how we will measure the elongation for different mass, that I will show you. So, I have here mass, I have here mass. So, this is the 100 gram mass, and this also 100 grams. So, these force are 100 grams, and this rest of the mass is 50 gram, is there 50 gram. So, initially I kept without any mass or whatever this initial this mass is there. So, I have kept this indicator. So, needle point at 0, needle point at 0, right. Now, this is my initial reading. Now, I will put say okay, let me put 100 gram first, let me put 100 gram first. Okay. Let me put 100 gram first, and then just let it be stable, it is vibrating. So, then I have to take reading. So, what is the reading? So, from here you can take this reading is 1.2 centimeter, the reading is 1.2 centimeter. Okay. So, then I will note down for mass, this is 100 gram, and this extension, that x reading is 1.2 centimeter. Okay. So, then I will put another mass, say another 100 gram, another 100 gram I will put. Now, this for that is for 200 gram is now, I think this sum is it is touching this side. So, I think this 200 is too much. So, let us vary with 50 gram. So, 100 gram is there, then I will put this 50 gram, I will put this 50 gram, okay. I will put this 50 gram, and then reading I will take the reading. Okay. So, it is around 2.2 it seems, it is 2.2 it seems. So, this slightly I have to rotate it, it seems slightly I can slightly I have to that maybe So, then I have increased mass by 50 gram. So, now it is 150 gram. So, for 150 gram, what is the reading we have to take? It is yeah, let it be stable, it is fluctuating, just give it time, slight time, yes. Okay. Okay. So, it is between the 2 to 2.1. So, let us take this it is a vibrating I think with respect to 2. So, it is a reading we will take 2.0. Okay. So, this way I will just increase by 50 gram, I will put another 50 gram, okay. Then I will take this reading. So, I will put another 50 gram, then I will take this reading. So, this way I will take at least 5 to 6 reading, and then I can repeat this reading when I will reduce the mass. Okay. So, that means whatever the maximum for 5-6 mass we have put here. So, each mass is 50 gram, initial one was 100 gram. So, now I will reduce the, so for this mass what is the reading that is that I will take. Now, I am reducing the mass. So, during increasing the mass I will take the reading, and again during reducing the mass, I will take the reading. So, then I will get 2 sets of reading, one is when we are increasing the mass, another is when we are decreasing the mass. Then from whatever the initial velocity value, it was basically 0. So, if it is not 0 also it is fine. So, just initial reading we have to just minus from each reading, then you will get for each mass what is the extension of the or elongation of the spring. So, now your data is ready, this your mass now multiply with g. So, that will be mg. So, that is W. Okay. For different load you have this depression for during reducing mass, increasing mass and reducing mass. So, from there you have to take basically average elongation, you have to find out average elongation. Now, we can plot the graph for this load versus the elongation, and you will get a straight line, and from that straight line you can basically that this slope of the straight line will be the spring constant. That is what I showed you. This relation is W equal to k x. So, W versus x if you plot. So, this slope of the curve will be k. So, this way one can find out the spring constant. So, this is the static method. Now, there is another method, generally in our lab we prefer to do this experiment, that is dynamic method. Okay. So, that is the dynamic method. So, what is that method? Basically f equal to minus k x, that we know. Now, f is m into acceleration means d2x by dt square equal to minus k x. So, this d2x by dt square plus k by m x equal to 0. So, this is the differential form of simple harmonic motion. Okay. So, this simple harmonic motion, the differential form we write d2x by dt square plus omega square x. Omega is basically the angular frequency of this spring mass system. Okay. So, then this omega square is nothing but k by m. So, and again omega equal to 2 pi by t, t is the time period. So, omega square equal to 4 pi square by t square equal to this k by m. So, this relation is telling that, so if I rearrange this relation, I can write t square equal to 4 pi square by k m. Okay. So, here you can see, so to find out the k value, okay, I experimentally I have to measure time period of oscillation for a particular mass. So, in this experiment in dynamic method we will just load different mass, and for each mass what is the time period that we have to find out. And then what we can do? So, okay, here one can consider the initial mass of this one. So, without any mass put here. So, that if it is m 0, then also there is no problem. So, if it is there, if we consider this initial mass m 0, so then basically this m will be replaced by m plus m 0, then t square equal to 4 pi square by k into m plus 4 pi square by k into m 0. Okay. So, this is the constant term as if it is c, and this is this is also constant, and this will be the slope, right. This will be the slope, I think SLOP. So, R is there. So, there is a mistake. So, it will be slope SLOP. So, then for different mass, this is the variable, I will measure the t. Okay. Then if I plot t square versus m, then I will get a straight line, and that straight line will not pass through the 0, it will cut the y axis. So, this will be the intersection of the y axis, okay, means t square axis. So, from t square versus m graph, we can find out the slope of the curve, and the slope of the curve will be 4 pi square by k. So, then k equal to 4 pi square by slope of the curve. So, from plot t square versus m plot, we will get the slope of the curve, and this is the constant. So, we can calculate k. Okay. So, now only experimentally we have to measure the time period for different mass. Okay. So, at least 4-5 mass you can do, because we have to plot graph. So, for this we need stopwatch. Okay. So, this is the digital stopwatch. Yeah, it has start and stop button here. Okay. If I just press it, so it started. Okay. It is the changing. So, it is yeah. So, it is changing second in second. So, we can get the reading in fraction of second also, but we do not need in fraction of second. So, here basically we will take least count as a second. So, 18, 19, 20, so it is changing. Okay. Now, I can stop it. Okay. Then I can read the reading. Okay. It is 23 second and some other 87, it is a fraction of a second in, so that we will ignore it. So, this is the reset button, I can reset it. Okay. Then start, stop, reset. Okay. So, this we will use to measure the time period. So, what is the time period? So, for a complete one oscillation, what is the time it is taking? So, that is the time period. So, in this case what we will do? So, it is difficult to just take time for just one oscillation. Okay. So, if it is the starting point, one complete oscillation will be just it will go down and come back at the initial point. So, this will be one complete oscillation, then it will be repeated. So, what I will do? I will just count number of oscillation, count number of complete oscillation starting this watch, and say 20, 30, 40 oscillation I will take, and then stop it, and then I will take this. So, total time taken for this 20, 30 or 40 oscillation, then for one oscillation. So, this total time divided by this number of complete oscillation, I will find out that is the time period. Okay. So, that I will repeat the experiment for different mass. So, let us start the experiment. So, here first I have to put some weight. So, this is the initial starting point. Okay. This is the initial starting point, and so in this case I do not need scale. So, just I will put, so this whatever the its weight I do not bother. So, if initial weight is say if it is m 0. So, as I told because of this we will get the intersection at y axis, but I do not bother that one. So, only now I will put weight say 100 gram, this is the 100 gram, okay, 100 gram. Now, for 100 gram weight 100 gram plus m 0 something is there, for that what is the time period that I want to find out. So, what I will do, I will just disturb it, just I will elongate it slightly and then leave it. Okay. Then now, I have to measure the time period, So, in convenient way I will start it, Okay. So, it is very difficult to measure because it is too fast, but you remember that relation between time period and this relation between the time period and the mass is basically here you can see it is time period and mass is the square of the time period is basically proportional to the mass. That means, if I increase mass, time period will increase. Okay. Time period will increase means for a one oscillation it will take more time. Okay. So, in this case it is taking less time. So, and for me it is difficult to measure also, too difficult to count it. So, from this knowledge what I will do? I will increase the mass for taking the reading. So, let me put another mass. Okay. Let me put another mass of 100 gram. So, this is 100 gram. So, now you will see this is 100 gram. Okay. This is 100 gram. Okay. Now, it is 200 gram. Now, for 200 gram plus some initial mass. So, for that you see that interestingly if I just disturb it, you see now its time period is higher. Now, I can easily count if its starting point is this. Okay. So, if start from the down. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So, now I will start my clock. Okay. So, when it is down then I will start. Okay. Start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So, just I will stop it. Okay. So, you see starting and stopping. So, at these two point I think there will be some mistake. So, to distribute this mistake over this total count. So, it is always better to take higher number of count. So, I have taken 30, but you can take 50. If you take 50, your result will be better. So, here I can see for 30 count. So, this reading is 21 second. So, in 21 second this 30 oscillation. So, for one oscillation, so what is the time? So, 21 divided by 30, right. So, that will be the time period. So, this way for different mass we should repeat the experiment. So, this I have done for 200 gram, then I will increase by 50 gram. I think I will put this way, I increase by 50 gram. So, now it is for 250, it is for 250. Okay. Okay. Now, again just I will reset it, I have to be ready. So, again for 250 gram mass I just disturb it. Okay. You see again this time period now becoming higher. So, it is becoming easier to measure, error will be less in counting. So, I will start. So, okay. So, when it is down I will start it. start 1, 2, 3, 4, 5, 6, 7. So, this way you take 30, 40. So, this time probably 30 is good enough. So, this way I will take 30 count and stop it and take the reading, right. So, find out the time period. So, what we are doing? So, at least I need 5 to 6 data point, okay, because I have to plot graph and it is straight line. So, 5 to 6 point will be good enough to draw a straight line. So, for that way I will just add the mass here and find out the time period. Also you can do in just reverse way also, we are decrease. So, that I do not think we need, because we are not taking reading here. So, just increase the mass and for different mass you find out the time period. Okay. So, now we will do calculation, we will find out the time period square of the time period and versus this I think versus this mass. Okay. So, we will plot at x axis this mass and y axis t square. So, t square versus m graph, that will be straight line, and now from straight line how to find out the slope, you know, I will show you that calculation, I will show you and how to find out this k, that I will show you, but this from this graph basically you will find out the slope. Now, 4 pi square by slope of the curve, then it will be your spin constant. Okay. So, I will discuss about the calculation and other this error, how to calculate error in this measurement. So, that I will discuss in the in next class. So, I will stop here. So, this is the very nice experiment for this for determining the spin constant. So, thank you for your kind attention.